Hello, greetings from Southwest Research Institute in Antonio, Texas, and wanted to say a quick thank you for the opportunity to give this presentation today. On behalf of my my fellow workers on this project, David Wieland, who's my section manager in aerospace structures, and Clint Twing, who is the section manager for non-destructive inspection here at the Institute. We did this project a few years ago and thought it would be a good opportunity to give a presentation about some interesting testing we did. First, I'll present a little bit of an outline. I'm going to go through these first few slides a little quickly. They're mostly background, a little bit of the purpose, and then as I get into the test approach and a little bit on the focus item, a little more interesting topics on fatigue and durability correlations, and then a couple of conclusions that we presented to our customer. A little background on the T-38. It's a supersonic trainer designed roughly 60 years ago, and first damage tolerance analyses were done in the late 70s. Of course, this aircraft was developed prior to our U.S. Air Force damage tolerance requirements. So that analysis was performed. The usage has changed over the years. We also do flight data recording. So we've been monitoring the usage of these fleets for the past 35 or 40 years. The usage has changed. And of course, as typical with military aircraft, the usages tend to get more severe. The two major usages that are routinely analyzed for this airframe are the introduction to fighter fundamentals, IFF, you'll hear me refer to that a little bit, and then specialized undergraduate pilot training, which is a little more moderate usage, not quite as severe. And we are expecting this aircraft to remain in service at least 10 more years, maybe possibly 15 to 20 more years. So the purpose was to perform full-scale durability testing to evaluate the latest legacy wing, which is we call the -29, it's the latest. There is a new wing coming online, and one of the purposes that we had for this test was to come up with replacement rates, projections for going to the next model wing, which I may refer to in the future as -33 during this presentation. So we tested two wings, set up two full aircraft tests with the wings attached to fuselage test articles for compliance at the wing root. We did an update to the durability and damage tolerance analysis as a result of this test and findings on the test results. And then looking at, as I mentioned, replacement rates for the -29 wings to the -33 model. So our test approach, our current usages for the T-38, this spectra plot gives you an idea, normal load factor plot showing the cumulative occurrences. So you can see that the IFF is substantially more severe than the SUPT data, and this was flight data we developed in the early 2000s timeframe, and both usages we confirmed through review of fleet-wide LESS data for comparison prior to applying the spectra to the test articles. So an overview of the test approach. Our wiffle tree design was one-sided. We had 10 push-pull wing actuators per side. Note that the aircraft, as shown, is inverted. So it allowed us to do all of the loading from the top skin, pulling down, and of course all the loads were accounted for that inverted aircraft. This was really nice because it allowed us to inspect the lower wing skin completely bare, did not have any test apparatus to remove every time we had to do our non-destructive inspections. So this made the inspection cycles much faster as compared to prior tests that have been performed. Just a summary of our test components. We use the MTS Aero ST controller with the AeroProbe software. Upon receipt of the test articles, we performed baseline inspections, NDI, both wings, with thousands of fastener holes to be inspected, milled pockets, machined edges, all of the significant structural details were inspected, and any results addressed prior to applying loading cycles. The test inspections during the testing were performed according to the technical orders. The -6, it shows the intervals to be inspected, and the -36 technical order describes the non-destructive inspection methods to be applied. We did round the inspections to the nearest 500 test hour blocks, since our test blocks were basically in 1,000-hour flight sequence blocks. So as an example, if a technical order -6 inspection was required at 450 hours, we would round to 500 since it was convenient for the blocks of testing. We did apply magnetostrictive sensors where they were placed on the lower wing skin to do some monitoring of the lower wing skin as the test was accumulating flight hours. One thing to note, the IFF wing had approximately 2,000 hours of prior service prior to being selected for a test article. And then the SUPT wing had less than 1,000 hours. So they did have some in-service time prior to the start of the test. That's the reason for the extensive inspections during the test. So just a quick overview of the wing setup. You can see this is kind of a time lapse. You can actually see the various deflected states during loading. So the IFF wing test, quick overview of the test results. We found multiple cracks at fastener holes before the test, and those were addressed. Where holes were found cracked, monitoring of cracking continued through the test. At 1,500 test hours on the right-hand side, the 66% spar is the aftmost spar of the primary wing box. And we found one crack there. Typical field level repair was installed. And then at 2,000 hours, we found several indications during our NDI. The left side 66% spar, pretty much symmetric to that first location. Same repair type was installed. The left side fatigue critical location was cracked, and we added a crack gauge to monitor growth. So we did get some crack growth behavior monitored during the test. And then another hole was cracked near a known FCL, and a blind fastener was removed, and the hole was oversized. At the completion, at 2,500 hours, we found a large crack at a relatively new FCL, which is one of the real drivers of the test, was to find potential new locations on what now amounts to be a fleet leader by our fatigue testing, and looking at new locations was a real goal. So we installed a double repair at that location. Crack was found at the lower skin radius on the left side. That crack was blended out, again, per a typical repair technique that would be used for a field article. At 2,750 test hours, the right wing failed. Large crack at a new milled pocket location that was not prior location for fatigue critical evaluation. The left wing milled pocket was also cracked, but not as long a crack. So together as much meaningful fatigue test data at this new location, the test setup was reconfigured to only load the left wing outboard of wing station 64.8. And then an additional 370 hours, flight hours were accumulated so that we could gather knowledge about that test, that crack location. Again, SUPT wing test now, again, a view showing the undeflected state. It's basically grayed out, and then the fully deflected state with time-lapse photography. So overview of the second test article. The fastener hole cracking began at 1,500-hour inspection and continued throughout the test. And at 8,000 test hours, right-hand 66% crack, very similar to to the IFF test article was found and repaired at 9,000 test hours. Multiple cracks were found at wing station 64, which 64.8 is the rib on which the landing gear are attached. So it becomes an important structural article and a place for load discontinuities. And that was just after the 15% spar, which is the leading edge spar. For that, we wanted to give our customer options on possible repairs going into the future. So the Air Force research labs were invited in to install some bonded repairs. So we did have some composite bonded repairs installed, and those were evaluated throughout the remainder of the test. At 9,500 test hours, we had again the left-hand cracking at 66% spar at wing station 52. Looking to be a very, very typical location and very representative of what we find in service aircraft. Both left and right-hand sides had cracks at an existing FCL, a nut plate hole, and those were addressed or monitored. So here's a little bit about the bonded repairs that were mentioned on the SUPT flight article, or test article. Bonded repairs were installed at 9,000 hours. On the left, we show the setup of the curing process. Pictured on the right is the strain gauge bonded repair over the cracking location, and that was continued to be monitored, and we did that repair on both sides. So the test continued, and at 18,500 test hours, a doubler repair was installed for the right-hand side lower wing skin. And at 18,700 test hours, the right wing failed. At the crack grew from underneath the bonded repair, installed at 9,000 hours. And in the view below, you can kind of see the crack continuing out from under the bonded repair here and continuing aft. So the real important part of the test, the results and the new fatigue critical location that was determined was a crack nucleating out of a milled pocket. This was an internal milled pocket on the lower wing skin, and this determined to be a new fatigue critical location. It appeared on both sides, and the constraint conditions for the wing test were then modified in order to continue the testing. As I mentioned, we got an additional 370 hours and a crack beginning at the milled pocket near the no FCL on the left side. The crack reached a critical length and failed the wing box. Picture of the crack nucleation area is shown below, and it's a composite of multiple images from our fractographic labs. So on the another focus item is taking that new FCL and looking at our durability and damage tolerance analysis update. We looked at the test failures and teardown findings. There was a post-test teardown of the entire wing. So we looked at all locations, even those that weren't determined during NDI during the test. We found the new FCL milled pocket on the lower wing skin. And also we updated a legacy fatigue critical location at a more outboard milled pocket that was more of a known quantity. The IFF and SUPT durability correlation was then done for cracks near the new FCLs, and a montage of the second or more longer milled pocket crack face is shown below. Again, much longer crack for this article and a little bit slower growth during the process. So a little bit more detail about what this milled pocket cracking looks like. It's at wing station 64.8, and the IFF wing's first failure at just over 4,600 test hours was at the detail, and the crack proceeded forward. So we began to look at this compared to our damage tolerance analysis. and we looked at the standard usages that were not scaled to the IFF test, just at the normal growth rates. We used strain gauges on the SUPT wing to develop stress to load relationships for our crack growth analysis as we get to the next step. We developed stress check finite element model of the location and the initial crack growth analysis. We could not get a crack to grow from a 0.005-inch half circular crack. And we, looking back at our fractography, we determined that was not sufficient. So we used a highly elliptical crack assumption and having much higher stress intensity through the thickness direction, and proceeded to complete the durability and damage tolerance analysis. So in comparing our crack growth analyses to the crack results in both the milled pocket locations, we could see that the test data, and represented by the dots, was at or above the crack growth analysis. So we were happy with that result, and then we moved on to durability correlations. The JSS&G is a joint service specification guide that is supposed to be followed for durability analysis for the U.S. Air Force follows that requirement. For the T-38, we had a durability approach based on the fracture mechanics models that had been developed using an initial flaw of 0.005. So for the durability correlation on the IFF wing, we had nearly 2,000 IFF hours on it prior to testing. The -29 wing then tested for 2,750 additional hours. We had a right wing failure, but the test continued. Wing reconfigured to test left side only, and so we got an additional 370 test hours on the left wing. The SUPT wing had almost 1,000 hours initial usage from fleet. The wing failed at 18,700, and the total SUPT time was over 19,500 equivalent test hours. Now we looked at comparing results for each lower wing skin fatigue critical location. So for the severe usage, we had our crack growth model, and it produced this curve, and the test results were much further to the right. So we knew we were conservative, and this is for a cold work fastener hole. So very, very conservative. And again, for the moderate usage, very similar result. And so we're happy with those, even though we couldn't take full advantage of the cold working. And analytically, we at least know we're conservative in our evaluation. For a non-cold work fastener detail, we're a little bit closer, but still conservative. Our severe usage curve and our severe usage results on the black dots. So we're still slightly to the right of the curve. For moderate usage, the dashed red line and the results there, and the X's are the test results, cracks, and showing again below and to the right of the curves. So we're conservative in our crack growth analysis, durability analysis. So in general, the durability analyses correlates well to the test results, and correlations for cold worked holes were very conservative as expected. And the single correlation that was very unconservative initially was for the legacy milled pocket fatigue critical location, and a reevaluation of the mechanical testing results and analysis methods were accomplished. And we updated the analysis using our test results, and the correlations were much better. So in summary, both IFF and SUPT legacy -29 wings were tested to failure, and the results were that a new FCL was found, An inspection time compliance technical order was a result, and with improved NDI procedures that were developed during the fatigue testing of the wings. And as that was implemented in the field, no cracks were confirmed at the wing station 40 location for the milled pocket crack, which was good, but new schedules were developed for the technical orders for field aircraft, for the Dash 6 and Dash 36 inspections. The durability analysis correlated well with test results, and the test results were used to update economic life estimates and planning for the purchase of new wings. Unfortunately, we're not allowed to present those economic life results, but the Dash 33 wing over the past 2.5 years since the completion of this work, the economic life predictions have kept Dash 33 wings available as they've been needed in the fleet. And that completes my presentation.